Okay, so welcome to this second part of my presentation on efficiency measures. And in this one, we're going to focus on how to measure efficiency when we have prices. And also we're going to focus on efficiency measurements over time, so the dynamic efficiency. So let's open up the slides. So what can we say about efficiency with prices? I have an illustration here that will give the main insights actually. So assume that you have a problem where you have one output and then you have two inputs. Input one, which could be OPEX or something else, and output two, which could be CAPEX or something else. It can also be physical, of course. This actually normally would make more sense if you have physicals, because then you have real prices. It could be like doctors on the x-axis and nurses on the y-axis. Now, let's assume that we have a company J that we want to evaluate. And we also have a technology, which is actually, in this case, a piecewise linear one, which is spanned by the firms A, B, C, and D. If you want to evaluate J, what we have seen so far, if you want to use Farrell efficiency, you basically try to make the largest contraction of both of its inputs, so that you proportional contraction of both inputs, so that you get to the frontier. So it's going to bring us from this point here down to this reference point here. And technical efficiency is really a matter of what is the length of this piece, this line here, divided by the length of this one up here. So, so that's technical efficiency. You can also say that it's like the minimal input divided by the actual input. Okay? And in this case, since we are doing proportional reduction, it doesn't matter whether we measure on the x-axis or on the y-axis. So one way to calculate the saving potentials in this direction is to say it's 75 divided by 120. Or you could also say it is 84 divided by 135. It will give the same ratio because you do proportional reductions. So that's basically this idea of technical efficiency, as I write over here, it's like the minimum input divided by the actual input. Okay. Now, if you're at this point here, another way actually to calculate this, you could say, is also that's also the cost of this point compared to the cost of this point. It's actually the cost of this one here divided by the cost of this one. Because since you're using the same prices and you do proportional reduction, you could actually move this into cost levels. So you could also calculate the technical efficiency in this case as the budget needed to produce at the reference point, which is 117,000 Swedish crowns, whatever unit we use, and divided by 187. That's another way to calculate technical efficiency in this case. Okay. But looking at it and assuming that we do have prices, and this is a price plan or a budget plan here. So what you see here is that it is relatively steeply sloped. So it means that you have to give up little of this one to get a lot of this one. So it actually it sort of indicates that input one is more expensive than input two. So this is actually not an optimal solution, because you could have lower cost had you moved to the point of tangency between the budget line and the IC point, which is point number D here. Okay, so you could say that there are some allocative inefficiency here. You haven't allocated your inputs. You haven't allocated the budget probably between the two inputs. And the way that we measure allocative efficiency, that's like the minimal budget compared to the actual budget in the technically efficient point. So you could compare the budget here, like 63, to the budget here, 117. And that is normally what is called allocative efficiency. So it's the budget, so it's the cost of the least cost point compared to the cost of the technically efficient point. Okay. So we have, we already talked about this. Okay, so we also have, like we talked about cost efficiency. which is like the minimal budget. So that is the budget for this point here, compared to the actual budget, which was it was this point here, and so the budget here was 187. So it's 63 divided by 187 as written down here. So that's another measure of sort of the amount of inefficiency that takes into account that you both have technical inefficiency because you could move from here to the frontier, but you also have an allocative inefficiency because you haven't chosen the right mix of the inputs when you take into account the relative prices of those inputs. So if you look at this, you can actually see that the cost efficiency, the minimal cost divided by the cost of this point here, that is actually equal to the technical efficiency, which you get from Farrell by moving from here to here, and then multiplied by the allocative efficiency, which is the gains you get from moving from this point, the cost gains you get from moving from this point to this point here, or from this point to this point over here. If you wanted to just look at everything on a straight line, since the cost of this point is the same as the cost of this point, you can say that cost efficiency is comparing this point to this point down here. Technically, efficiency is just comparing this point to this point here. So that's another way to look at it. So you can see as soon as you have prices, you can do a lot of extra calculations where you do not only require the firm to be on the frontier to be technically efficient, but you also require them to be at the right place of the frontier, which is a question of allocative efficiency. So I'm going to details what I've just talked about in a few simple slides, and to clarify this, because some of these decompositions is actually very useful, like this one down here, where you say the cost efficiency is a combination of technical efficiency and allocative efficiency. And let's do that right away. So here I've sort of cleaned up the picture. I have a production plan. My present production plan is here at X. I have an ISO quant here. I have an ISO cost line, a budget line here. And so the cheapest way to produce whatever output we're producing, which is fixed in this picture here. So we just look at the input side. The cheapest way to produce that is to use this input combination X star. And that will give me this cost line, this cost level here. So cost efficiency is really the cost of my present input mix compared to the cost of the minimal cost index. And it is always on the input side, we always say, what is the minimum compared to the actual level? So it is like the minimum cost, which is WE, which is the price vector for inputs, multiplied by X, and then divided by WE multiplied by the price vector X. So that's cost efficiency. This is just a fancy way of writing cost at this point cost at this point divided by cost at this point here. An interesting thing you can do is you can rewrite this here by just inserting the price of the cost of V tilde. So if you divide this one with V tilde, and then you multiply with V tilde again, they can cancel out here, and you're back to the original one. But this one is an interesting concept, because what is it really? Well, you see that the last bit here is the cost of this point divided by the cost of this one here. So as I say, that's actually technical efficiency. It doesn't really matter which price vectors you use when you want to. You can always calculate technical efficiency, not just as the proportion, the factor you can use to proportionally reduce all the inputs. You can also say that, okay, it's the cost of that on my present level compared to the cost on the projection point I get when I move towards the 0 point. Okay, so that's basically technical efficiency. And now the first bit here is the cost of X star divided by the cost of X tilde. Okay, so this was what we before called allocative efficiency. It's the cost of, you have already reached the technical efficient frontier, but you haven't located yourself at the correct frontier. So this is the cost here divided by the cost of here. So actually we do have this notion of cost efficiency, which is Minimal cost compared to the actual cost, and we can decompose that as first you have to get to the frontier, which is technical efficiency, and then you have to get to the right point on the frontier, which is allocative efficiency. In terms of interpretation, we often use sort of phrases like this. Cost efficiency requires not only to be on the frontier, which is technical efficiency, which we can say basically means do things right. Whatever you do it in an efficient way. So you can say here you are doing stuff at an efficient way, technically, okay? But the other one is do things right. So whatever you want to accomplish, you need to do so in the smartest possible way. It's not enough to just run as fast as possible in one direction. You should actually also think about running in the right direction. So that's doing things, doing right things. So by just these almost similar formulations, we can emphasize the difference between technical efficiency, which is to do things right, and allocative efficiency, which is to do the right things. Basically, we need to use the resources in a technical efficient way, and we need to choose the mix of resources that is the smartest one, okay? So that was the cost and input allocative efficiency. Relative, you can do exactly the same on the output side. You can do what we could call revenue efficiency, and that will now be what kind of revenue could I, what's the maximum? Okay, my present production output is here. I have the output isoquant here. The best place, if I can sell my products for the relative prices indicated by the slope of this line here, is revenue line here, is this point y star, okay? So the revenue efficiency is what revenue would I generate had I located myself out here, divided by the revenue I generate down here, which is what I write here, okay? Remember, now we're on the output side, so we tend to sort of measure things so that large number are a sign of inefficiency. So in this case here, I get a bigger revenue here than I do here, so therefore I get a ratio of revenue efficiency which is larger than 1, which means that I could have expanded my revenue, okay? And therefore it represents inefficiency. Now again, you could first consider moving your production plan out here proportionally to the frontier, and then only later adjusting the mix of services you provide. And this is what I do here. Here, I first move from Y to Y star. So that's technical efficiency. This bit here is technical efficiency. And since it's on the output side, it's equivalent to the Farrell output symbol I used before, F. So this is Farrell output efficiency. And then this one here is the revenue I generate in this point compared to the revenue I generate in this point. And that's like an allocative efficiency measure. A large one means a large allocative inefficiency. I could have increased my revenue quite a bit had I chosen a mix of services that is perfectly aligned with the prices in the market. Okay, so you can again measure revenue efficiency by comparing actual revenue and maximum revenue, and you can decompose that in technical change and in an allocative change. And again, we can interpret it like before. You have to do the things right. Whatever you produce, you have to produce as much as possible. But the other thing you have to do is you have to do the right things. You have to choose the right mix of products to produce. You need to run fast and you need to run in the right direction. So again, it also means that you have to use your resources in a technically efficient way, and you have to choose the right mix of outputs so that it really matches the prices on the market. So that's revenue and output allocative efficiency. There's one more concept I would like to introduce, and that has nothing to do with prices. Actually, it's still a technical efficiency measure. So I could have put it in the previous section, but it was already relatively long. I want to talk a little bit about scale efficiency. So here I have a case here with 4 companies, A, B, and C, and D. and you see they have one input and one output. You can of course do these things also in more dimensions, but it's just easier to get an impression by just this simple picture. Now, what you see here is that company number D is inefficient. If this is the technology, and we assume it is, then D is inefficient because it could have reduced its cost from 120 all the way down to 75. So the cost efficiency of this guy is input cost efficiency is 75 divided by 120. Okay, so that's 62%. Now the reason we cannot move any further is because the technology looked like this. But there's an interesting thing about this point B, and that is that point B is actually the place where you get the most output per input unit used. So that is kind of the place where you get the most gains from your effort. And if D had the same possibility of getting output per input unit as we have in B, then we could have moved all the way down here to A. Okay, so you can say that this B is kind of an optimal scale size, because ideally you want to get as much output per input unit as possible. And if you are down here on the frontier, you have a relative, so basically that output per input, that is the slope of the line from here to any point. So here you have a relatively low output per input ratio. Here you get a bigger one, you get a bigger one, you get a bigger one. And here you have the largest one, and then it starts to fall again. That's actually why we also later will call it a variable return to scale technology, because what we see is that first the return to scale is increasing, and then it is decreasing, and returns to scale is output per input unit. So first it increases and then it decreases. Anyway, what I wanted to say is in the event that the other companies, like also company D, could have enjoyed the same output per input efficiency as the optimal scale size B does, then we could have saved all the way down to this point here. So in this case, we would have received we would have gotten a technical efficiency of 70 divided by 120. That's actually will actually be the technical efficiency in a CIS model, country return to scale DEA model. What I've illustrated is the main one here is a DEA variable return to scale model. Okay, so you could say that, okay, you can move from here to here by just using less of your inputs. And have you had the extra opportunity of enjoying a higher returns to scale, you could have moved from this to this. And that is what we call scale efficiency. So that is 70 divided by 75. That's the minimal input needed in the CIS technology divided by the minimal input needed in the actual technology, or the VIS technology in this case. So you could start to think about how big is this, and if that is big, it's because you are located far away from the optimal scale size. Imagine, for example, you're down here, then you could move here by just becoming technically efficient, but then you could move just as much or even more if you had the optimal scale size returns to scale, you can say. Okay. So we have this new notion of scale efficiency, and it is really, and you get this decomposition that the efficiency according to the CIS technology, this one here, is the efficiency according to the VIS multiplied by this extra saving you can get from this point to this point. Okay. So you will see actually in many cases and many studies, they will calculate efficiency, and they will also calculate scale efficiency. And then if you have a low scale efficiency, they will say that, these companies are somewhat inefficient, but that's mainly because they are operating at a bad scale size. They do not operate at the optimal scale size, which is where you get the most output per input unit. So that's a quite common thing to report and to get an idea also about the whole sector. Do we have a sector with a lot of too small companies, or do we even maybe have a sector with also several large companies? So a naive way of calculating possible improvements in the structural efficiency of the whole sector, the sectoral efficiency or the structural efficiency, which we have another presentation on, is actually to look at the scale efficiencies. So if scale efficiencies are far away from 1, then there seems to be some potential gains from merging units or from splitting them up. But one has to be really careful, because this is easy when you just have one input, one output, but in reality you might have many inputs and many outputs, so it also plays together with the scope. But it's actually a quite common way to look at it, and as I kind of indicated, it's not always done correctly, but at least now you have this concept of scale efficiency and technical efficiency. So to sum up in sort of more conceptual terms, we have technical efficiency is the question of choosing the right methods and procedures given whatever inputs and outputs you're trying to produce. Allocative efficiency has to do with choosing the right inputs, the ones that are cheapest way to accomplish what you need in terms of the output. So choosing the right mix of inputs or choosing the right mix of outputs so that you can actually maximize the revenue. It doesn't make sense to produce a lot of product that don't really sell very well. And cost efficiency is the combination of being both technically and allocatively efficient. So you have cost efficiency is technical efficiency multiplied by allocative efficiency. You could also have, if you have a model with inputs, physical inputs, you have the prices and you have the outputs. You could then construct an alternative input, namely the cost for each of these bundles. And then you just have a one input, namely cost, and multi-output model. And then in this model, you could do normal technical efficiency measures. But because you already have just one input, namely the aggregated cost, that will also be the same as cost efficiency. Another important thing to note is that if you ask people to have a high cost efficiency, you are asking them two things. Not only should the technicians and the engineers, they should be very efficient at fine-tuning the production and getting the most out of the whichever inputs are being used. It's also, you're also asking the economists that procure the product, the resources needed, and the sales department that are supposed to sell the product to get the most out to sell the product in the best possible way, and to procure resources in the cheapest possible way. So you're kind of putting more demand on an organization when you evaluate them with cost efficiency rather than with technical efficiency. Here, with technical efficiency, you're only sort of focusing on the engineering part of it. With cost efficiency, you're focusing more on a holistic view of the company. And that's also why we know from these formula, since all of these are numbers less than 1, both technical efficiency and allocative efficiency, then the cost efficiency will always be lower than technical efficiency. Or technical efficiency is larger than or equal to cost efficiency. Let's put it like that. You can do the same on the output side. You can do the same where you both consider where you go from looking at physical inputs and physical outputs, you use the prices, and then you can have cost on the input side and revenue on the output side, and you can also do, in that way, you can also do profit efficiency. And the last concept I introduced was this idea of scale efficiency. It has to do with you want to try, ideally if you could decide yourself on the output level and your input level, you would like to choose the right scale of operation where you have the maximum output per input unit, or if you have input, then you have the minimal average cost, the minimal cost per unit being produced. Okay, and we have this relationship here. The efficiency score you get in the CIS model is the one you get in the VIS model multiplied by the scale efficiency. Okay, it's time for some questions, and it's also time for if you're interested to try to do these some of these analysis on a real data set, you can do that. For example, without any programming in the interactive benchmarking software on ivanweb.com, and then log in as before. But let's break for a little while and think about those, and then I'll return in a few seconds and continue with the dynamic efficiency. Okay, so let's continue with dynamic efficiency, and just to give you an idea of what we're looking for, you can return to this simple picture I've used before. So let's assume you have outputs and you have inputs. You have a firm that is located here. You have the cost function at time 1 here, and you have the cost function of this sector of this technology at time 2. What we've looked at so far is cost efficiency and technical efficiency, and it has to do with measurement of what we could also call incumbent inefficiency, the existing inefficiency in the company. Taking a picture right now, what's the inefficiency in this company? That's basically the distance from here to here. Now, over time, the technology is likely to change. So if we have technological progress, the cost function gets lower, and you might get down to this one here. So we call this change in the frontier, we call that naturally frontier shift. And now it gets interesting when you have like 2 or 3 or 4 or 5 periods, because the question is, does this guy get closer to, he might actually improve from year 1 to year 2. He might go down here, but in the meantime, the target you have to reach have moved even further away. So although he has improved, he all of a sudden looks worse in the next period. So it's really interesting to try to investigate what changes over time. How much does the frontier shift, and how does his location relative to the frontier, how does that change from period to period, which we call catch-up effect. So we have like a frontier shift and a catch-up effect. So to give a slightly more detailed focus on this problem of frontier shift and changes behind the frontier, I'll use this picture here, and we might just as well also introduce a bit of notation. So let's assume that E superscript I ST is the efficiency of I'll use these company number I in period S against the technology in period T. So I take the data from period S, but when I evaluated this firm against the technology as it looks in period number T. Okay. And now let's try to take, this is an illustration of what's going to go on. I have the company, it's the same company I'm studying in each period. I have the company at time S, which is the first period, and at time T, which is the second period, because S is for T. Okay, so when I look at it, when I look at this company here, when it's black, it's always in period S, and red is period T. So when I look at my company, I have a certain distance to the frontier, okay, corresponding to this black one here. So it's not too impressive. Now at time T, I moved from this point up to this point, and now actually my distance to the frontier is smaller. The length of this black arrow is smaller than the length of this black arrow here. So I've kind of catched up to the frontier, you can say. The problem is just that similar from time S to time T, there's also been a shift in the frontier. So now the frontier is down here. So while before I had a distance to state-of-the-art technology equal to this, I make some improvements, I get closer to the frontier. I'm also changing a little bit what kind of inputs I'm using, but I'm getting closer to the frontier. All of a sudden, the frontier has moved, and now I'm further away from the frontier. And this is what we'll try to capture using various indices. That is, how does my behavior change, and how can we decompose my score into something that is related to my my relationship to a given frontier and to a shift in the frontier. Okay, Before going into some details, let me just pause and note that this is really important, because sometimes it's not just important what the absolute level of efficiency is or inefficiency is. You can just imagine an incentive context, and you get an incentive contract. And now if you focus on the absolute level of efficiency, you're actually focusing, or the incumbent efficiency, you're kind of focusing on what you did in the past. An incentive scheme should ideally incentivize proper behavior in the future. So it might be interesting not just to look at the level of efficiency, but how that level of efficiency changes over time. And maybe it's more important to reward him for increasing his efficiency than for rewarding him in a given year for having a high efficiency. Now, at the end of the day, it becomes a little bit the same, because if you want to reward them for increasing efficiency, it also means that you end up rewarding them for getting higher efficiencies. I'm just not saying at the outset, it's not the starting point that is important. It's like the improvement if you're really focusing on incentives. You can also put it sort of more down to earth. If you're an incumbent management and you're just taking over a company, maybe, okay? So you're now the existing management, but there used to be a managers, and they have done really badly. Then your salary should not really reflect that they have done badly and handed over to you a quite inefficient firm. Rather, your payment should be dependent on how you can really improve efficiency in the future. So for these purposes, dynamic consideration is very important. You therefore also see in many contracts that if you have long-term contracts, there's normally a provision in those contracts that relates to how things are going to change in the future. There might be some price changes, there might be some changes in expected changes in the efficiency by which you can produce and productivity, how the frontier look. You want to incorporate that into a long-term contract, because if you do not, then the contract, the guy having to produce, for example, he will take all the gains from a future productivity development. So if I'm buying from such a guy, I might put in a provision saying that, okay, over time, I would like my cost to go down, because I do know that your cost will also go down. So you want to take this long-term perspective and incorporate some thinking about the dynamic development. You can also take a regulatory perspective. In the presentation on regulatory benchmarking, I showed you like the revenue cap formula, which could be sort of simplified to this one here. The revenue I'm allowed to have in a given period is my initial cost level multiplied by 1 minus xi, where xi is supposed to ensure that you catch up to best practices, to the frontier. That's the incumbent inefficiency part. And then the general x is supposed to measure this frontier shift. So the theme of what I'm going to talk about here is directly related to the items you want to put into a classical regulatory formula or contract with the utilities. Okay, so from a theoretical point of view, one of the most important indices you can use is the Malmquist index. And it's an index that works in a multi-input, multi-output context without having any prices to aggregate with. So normally if you have less pair or these kind of indices, you need some kind of a price index so that you can do some aggregations. But if you these classical indices, so the Malmquist don't need any prices, which is actually a very elegant property. And the definition is also quite simple. So the Malmquist index for my firm I from S to T is this square root. And it might look slightly complicated, but it's actually just the geometric mean of two ratios here. So if you have ratios and things that you will normally multiply, the way to take the mean is not just to take the average value, but it is normally to multiply them together and then take the square root. So it's called the geometric mean. So let's look at the first ratio here. What is that? That's my efficiency at time S. And up here I have my efficiency at time T. And the technology I'm using is the same. It's a fixed technology. So I'm comparing to technology number at time from time S. Over here is exactly the same. It's how I look at time t in the future divided by how I look at now. And the only difference is that here I use the technology at time t as the benchmark. And that's really, you just need to compare with some kind of a technology, and you need, and you don't know whether it should be an S technology or T technology. And so basically you try both of them, and then you take the average result to get out of it. Remember, if you have a high value, it means that you are, since this is input efficiency, a high value means that you're close to the frontier, so you're doing well. A low value means that you're far away from the frontier. So for example, if this ratio here is about 1, it means that at time t in the future, I'm closer to the frontier than I am presently, okay? So a high value here is good news. It corresponds to progress. It corresponds to me getting closer to some target I have, okay? So that's basically the idea of this one here. That's Malmquist index. So here's an example. The Malmquist is defined like here. Here I have an example here with S and T. And now I just need to figure out what to put into these, how to substitute these expressions with some real number. And let's just take, for example, this one here. In this ratio here, I'm always comparing to technology S, which is this one here. And so basically I need to find the efficiency of my firm at time t against this technology. So t is here. So the minimal cost of producing this output level, that is 40. And my present level is 50. So my input efficiency at time t, if I compare to technology at time s, is 40 divided by 50. Down here I have s time s against technology at time s. So it's this one here compared to this one, and the minimum cost is 25, and my actual cost is 45. So that's what I get down here. And similar, you can do this one here. And if you do this, you'll get a number called 1.423. And that really means that over time, you're doing better. And you can also see that really here, because you do have an increase in output from time S to time T, but the increase in cost is much more modest, okay? It's more modest than it is here, for example. If you had the same change in output, you would have an increasing cost of 25, or 15. You only have an increasing cost of 5. It's also higher than it would be here, because here you would have a cost increase of 4 plus 5, that's 9. And what you have up here is only increase in 5. So you actually, things are improving for you, okay? So that's good news. You're able to produce more efficiently, and you get more output per input in the future than you do right now. Here I have also an alternative example where you can say that, okay, at time, my cost, I'm producing some given output. Here my cost is first 4, and next period is 2.5. I have observation from others. The lowest cost in the first period is 2, the red one, and in the second period is 1. And then you can basically do exactly the same calculations here. This is a special case where these are special cases where you just have one input divided by one output. And in that case, one can actually reformulate this expression so that it just becomes a question of how much does the output grow divided by how much does the input grow, which is very similar to what a lot of economists will normally do when they calculate some total factor productivity. So they say that, okay, output has grown with 10%, input has grown with 5%. So 1.1 divided by 1.05, that's kind of the productivity gain you would have had. Sorry. One of the nice things about this Malmquist, which is sort of the total improvements But that improvement can come from getting closer to the frontier, and it can also come from the frontier shifting and you still getting staying the same distance to the frontier, maybe even coming closer to this moving target. So the cool thing is you can take this expression that you have, and now you can reformulate it like this. So what I've done is basically I put the inverse of this one inside the square root, and that means that I can cancel out terms, and then I end up with this inside it, and with this outside the square root. Okay, so you can rewrite my previous formula into this one here. And now we can interpret this as technical change or frontier shift, and as efficiency change. Okay, sorry. And efficiency change, which also means catching up effect. Let's just take the last bit here. This is my efficiency at time t compared to t technology divided by my efficiency at time s compared to the x technology. So if this ratio is larger than 1, it means that at time t I'm closer to the technology at time t than I was at time s to the technology at time s. So I've been catching up to the frontier. Okay, we call it efficiency change here, probably just called catch-up effect. The other one here is slightly more complicated to interpret, but then again, it's not so bad. Basically, what we do is at time t, we fix the observation. And now what we change is the technology. So here we're trying to measure how does the technology move. And the way we measure how the technology moves is we compare technology points to a fixed production plan, namely, in this case, the production plan at time t. And then we see how close is the frontier to this at time s and to time t. So we fix the observation, and you just look at how the frontier is relative to that observation. But you don't necessarily need to use the observation at time t to do that anchoring point or use this as a base for your measurement. You could also have used the observation at time s. And since no one is preferred to the, no anchor point is better than the other one, then you just take the geometric mean of the two. But really, this one is a question of how the frontier is shifting, and this one is a question of how my relationship to the frontier is shifting. Okay. Maybe just to explain to you, when you look at this, when you look at this, where was the formula? Didn't I have one? Sorry, this was the example. This was the example. Okay, if you want to just interpret this here, so basically, I'm looking at my performance at time t, and so it means that what happens if this ratio here is larger than 1? That means that this one here is larger than this one here. So it means that my performance is looking better when compared to the X technology than compared to the T technology. Why would that be the case? Well, that is the case if the T technology is further out. Okay, so you can do more in time T than you could in time S. So that's why a value of this one here, about 1, suggests that the frontier has been pushed, there's been technological progress rather than regress. Okay. Normally, it requires that you sit and then you look at it a little while, then you will see it quite clearly. So here's this numerical example where I split up this Malmquist index in 2 terms. I split it up in the technical change, so having to do with this frontier shift. So if you want to summarize the frontier shift, you'll say that it's 1.5. So there's been sort of a 50%, 50 or 60% increase in what is technologically feasible. At the same time, the efficiency change or the catch up is a little bit below 1. It means that I'm now in the future, I'm further away from the future's technology than I presently am to today's technology. And that's also what it's a little bit hard to see, but actually you can see this distance here is a little bit smaller than this distance here. Okay. So, but overall, there's still a lot of gain associated with going from here to here, because you also have this increase in the output. So here's a numerical example again. Here I'll also introduce these notions like frontier shift and catch up, instead of just technical efficiency and efficiency change. You can do exactly the same calculations. My cost at time S, my cost at time t, and this is the frontier cost at time t, and this is the frontier cost at time s. So that's the then you can try to recalculate this here just to get an idea of it. Okay. No, actually, normally we would say that it's type T. Just a second. Okay, so I just got a little bit confused. That's actually because my very first picture I went from black to red. So the first period was black, and then the second period was red. But I see actually in this example here, I've changed the color code. So S is the first period, and T, the black ones, are here the second period. So I apologize for that. It's not too smart to do that. You want to make things easy to follow. Anyway, just to close, I want to say that talking about Malmquist, you can try to play around with it in the interactive benchmarking software. Here's a data set you can try to use, and then I describe which model in this data set you should try to use, and then you can see that you can actually calculate both the technical efficiency effects of the frontier shift. You can look at the catch-up effect, and you can look at the frontier shift. And the reason there are two curves is that I'm doing it for a given firm, how does it develop, and then I'm doing it as an average for all firms. So that's the average are the green ones, and a specific firm that I'm analyzing is the blue one here. See, you'll see sort of numbers in the neighborhood of 1 or slightly above 1 and slightly below 1 at some points. So you can sort of see how efficiency changes, how the dynamic efficiency changes, and how that changes due to either frontier shift or catching up or lag, so off. Okay, I want to make a few more comments on the Malmquist index. You would actually like the index to be so that the improvement from period 1 to 2 multiplied by 2 with the improvement from 2 to 3 would be the same as the improvement from period 1 to 3. That's not the case. It's called the circular test, and this is not fulfilled by Malmquist, as it is actually not fulfilled by a lot of indices you will find, unless the technology has certain regularity called Higgs neutrality, something that the isoquants are moving very, very parallel to each other. So if you really want to do stuff, if you want to sort of do calculations over many periods, another idea is basically to fix the base technology and then compare performance in each year to that fixed technology. And of course, the problem with that is that then the results will depend on which one you might be comparing to, but that's another thing. It's actually, I put in a table here from a project we're working on right now about the impact of innovation, where we look at companies that do not innovate in a given year, and then they innovate the next year, and then we follow them. So they innovate in year 0, and then we follow them for 3 years, and then we see how their value added changes. Or the efficiency in a labor cost of the input and value added of the output model. And what you see, for example, is that if I introduce product innovation, so developing new products, that will give me a boost in my value added of all the way up to 53%. If I change this, introduce new procedures, make innovative procedures, then that will have an impact of 13% over a 3-year period. I will have organizational innovation, gives me an improvement of value added per resources used of 20%, and so on. So that's just an idea here. You see, the difference between a normal Malmquist, you will compare 0 to 1, 1 to 2, 2 to 3, 3 to 4, or whatever however you want to do it. And that's very good if you want to sort of see what's the likely yearly change in output. But if you want to sort of look at the cumulative effect, since this one doesn't really work, it might be better just to fix the base technology at time 0 and then always compare things to time 0 and then compare it at 1, time 2, and time 3 to time 0 all the time. Okay, so to summarize on Malmquist, the very good thing is that it doesn't require any price information on the input side or the output sides, and there's sort of no behavioral assumptions or profit maximization or anything involved in that. You can use the same logic with a lot of different technologies, SFA, DA, and other technologies. And there are many alternative decompositions. I showed you one decomposition in technical efficiency and another one in frontier shift and in catch up. But then a lot of scholars, it's like a national sport in this area, is to come up with other decomposition where you take this square root with these two factors, and then you try to insert something and divide by something, and then you get the square root split into another square root and some other number, and you can do that in a lot of different ways. So that's worthwhile to note that there are many decompositions, but I kind of gave you the classical one here. The problems, it fails the circular test as we talked about. My experience is also that you need a fair amount of data for this to really get robust results. Otherwise, you might get results where if you have only a few observations, you might get results where 1 year there's like a frontier shift of 20%, and the next year there's a technological decline of 5%. And of course, that doesn't really make much sense if you look at a real industry. You don't all of a sudden have these huge changes up and down. So it's a little bit, in my experience, a little bit unstable on small data sets. There can also be some feasibility problems because you're comparing an observation in 1 year against a technology from another year. And since if you do DA, it might actually not be feasible to use this year's technology, this year's production in the technology of another year. Okay, it can sort of fall outside that technology, and therefore some people will tend to just assume constant return to scale when they do these decompositions. But in many cases, it also works perfectly fine with the other ones. So I'm not so strong on that point. So I'm not so strict on that point. I want to mention another thing. Two other things. I want to say, okay, from a regulatory point of view, it's really cool. You get an idea of the incompetent efficiency that can help you set the XI. You get an idea about how the frontier shift that could inform you about the general X. So you could imagine that this is used a lot by regulators. It's actually not, but I'll return to that. What is important is also that you can use this similar idea of comparing frontiers and relationships to frontiers on a lot of other things. So for example, are the best practice in western part of the US better than the best practices in the eastern part? Or are the distance to the best practice, is that more varied in some states rather than in some other states? So comparison across regions, you can compare the how does investor-owned companies compare to cooperatives using the same kind of decompositions. You can play around with it and develop your own by being inspired by the Malmquist. And it's implemented in most standard packages for DA and related techniques, and also in our benchmarking package, of course. I want to say that although it is fitting really well into the classical revenue cap scheme in regulation, because it identifies the general X and the individual X, it is not always used. And I want to show you what is done instead and warn you a little bit about what is done instead. I also want to mention that if you move to a regulatory scheme like the yardstick scheme, so if you want to make a contract which is not sort of fixed prices, fixing the price development in the next 5 years, but you say that, okay, we make a contract and then we'll see next year what is a reasonable price, and next year what is a reasonable price. If you take more like a yardstick approach, then you don't need to speculate so much about how the frontier is shifting, because you're going to observe how it actually did change. So in that case, you don't need the frontier shift information if you just change the contract form. But let me explain to you briefly what is a lot of regulators are doing. So we have again like the classical revenue cap formula up here. My revenue at time t is equal to my revenue at time times t minus 1, and then I multiply with the price index because there'll be some inflation. I multiply it with I subtract this general productivity development, which is supposed to capture frontier shift, and then my individual requirement. Now the question is, how can you go out and find a price index, or which price index should you use, and how do you set this one? And actually, the price index you use sort of will have an impact on how you should set this X factor, and I'll try to explain that. Just to give you an idea, I've made a very simple model framework here. So we have production, and we use input X to produce output Y. The prices of inputs are W, the prices of outputs are P, like we've used in other slides in this set here. Let's assume now that you have your regulated sector, and this is the technology in the beginning, and then next year the technology looked like this, because we see some technological progress. You could say, for example, that instead of using X as the input, assuming that output is fixed, for example, you could say that instead of using X as the input, it's enough just to use 1 minus C times the input. Okay, so C has to do with the savings that come from having a better technology. Okay, so 1 minus C is equal to, in this case, the Farrell input efficiency, but let's call it C at this point here. Now the idea is that most of the time regulators, they'll just go out and look at a related industry, a market-based industry or sector, hopefully a competitive one. And so over here I have kind of the same numbers, I'm just using capital letters, but this is another industry. And this is the kind of industry that Statistics Denmark or some other national statistics authority is collecting data from. And I'm going to see if I can use some of that information to guide how I set these X's and the PIs. Okay, so it's the same story. If you have a case like I showed for my firm on the in the left part of this panel here, and I wanted to figure out how should I change my revenue from period t minus 1 to period t, you can say that, okay, it has to be increased by this A, which is, as you can see, it is the increase in input prices. Okay, so if input price goes up with 10%, then my revenue, my prices on the output side should also go up with 10%, unless there's some productivity gain. So if I have this C that I also assumed I have, then I can subtract that. So because then if I can use 10% less of resources, then the fact that they have become 10% more expensive doesn't really matter, it cancels out. So ideally, I would like to do this, okay? And now remember that assuming in the competitive industry, the output prices will change by how the input prices are changing minus how the productivity of this competitive industry is changing. And because of competition, these firms are going to shift all the productivity gains to the consumers, basically, because otherwise they can't sell their products. So assuming perfect competition in this index sector, then the output prices in the index sector is going to change with capital A minus capital C. And so we ignore, in this picture here, we ignore individual inefficiency. So basically what I would use in a regular, if I as a regulator goes out and I use a price index from a competitive industry, Okay. Then I will actually say, I will actually allow the revenue to change with 1 plus A minus C minus XGE. What I would, from a theoretical point of view, I would like the change to be 1 plus A small lower cap A minus lower cap C. Okay. So the question is, when is this one, this one giving the right number? So rearranging here, I can see that XGI needs to be this one here and this one here. And what is this? This is the price development, how input prices increase in the in the reference sector minus how they change in my sector. And this is how my productivity improves minus how the productivity improves in the reference sector. So basically XGI is not supposed to be just how the frontiers shift in the competitive industry. It is supposed to be the extra pricing increase in the index sector here, plus the extra productivity increase in the regulated sector, which is this one here. So that is something that is often misunderstood. You think that, okay, you can just go out and see how does productivity develop in some other sector, and then you require everyone in the regulated sector to follow that. But you have to be careful with that. And just to close with an example, so assume that you have like an economic or index sector change where you have a 1% increase in input prices, but you have a 3% increases in the productivity or total factor productivity. So you can produce output with 3% less inputs. In the regulated sector, you have input prices are increasing faster, but productivity is also increasing faster. Now, what kind of demand should you put on the company, ignoring individual catching up? Well, you should use the formula here. And so basically it becomes 1 minus 2% plus 5 minus 3%, which is equal to 1%. So basically what it says, this simple analysis, is that the regulated industry, it loses 1% from having higher inflation, because it was an increase in input price of 2 compared to 1. So it loses 1, but then it gains 2% in productivity. So in total, it should be able to do 1% better than the market sector. And that is why you should have this 1% here. Okay, so it is a misunderstanding that you can just import productivity development from another sector and use directly into the revenue cap formula. And it was actually a few regulators realized it explicitly, but it is something that was known from the very conception of this system, but it tended to be ignored. Good. Enough about this. As I mentioned, you can try this exercise here, but I just want to conclude, and then you can play around with it after that. We've covered many measures. You have technical efficiency without price information. We talked about Farrell, Shepard, the hyperbolic, how to handle non-discretionary inputs. You just make reductions in the other inputs. How you can, in general, choose another direction to move in. So you choose how important is to save it in these inputs, and how important is it to expand some particular outputs. So you can use a directional distance like that, or like an excess function, or that is actually what it was using in its active benchmarking also. If you have prices, you can do more refined and, frankly speaking, also tougher evaluations of the company, because you can ask for cost efficiency, revenue efficiency. Cost efficiency meaning that you need to have the lowest cost of providing the given services. Revenue efficiency, you need to maximize the revenue. Allocative efficiency, you need to choose the right mix of inputs and the right mix of outputs. And scale efficiency, you need to operate at an optimal scale size. We discussed that. And then finally, we talked about dynamic efficiency, talked about the Malmquist index and how that could be decomposed into a frontier shift and a catch-up effect. And we talked at the very end about the need to be careful if you want to just rely on productivity indices from other sectors when you want to make a contract, because you need to think about how prices in a competitive sector is a reflection. Output prices changes is really reflecting how input prices are changing there and how the productivity in that sector is there. So if you only allow inflation of the contracted product to increase with the inflation in the competitive industry, then you are implicitly assuming that they could have exactly the same productivity development as the competitive sector, and therefore you shouldn't have any extra productivity requirement imposed on the company. So that's was what we learned at the very end. And then finally, you might ask the following questions: which of all these measures should you really use? And it really depends on many factors. Controllability is an important one. Can you control your inputs or can you control the outputs? If you're utility, you normally cannot have much control over the outputs because it's basically demand driven. You just have to supply in the cheapest possible way whatever services is required. If you are in a have a short time horizon, you might not be able to change your fixed cost, but you can change your variable cost, to give 2 examples of controllability. So think about what can the unit you are evaluating actually control, because you should not make them too responsible for stuff they have no control over. It also has to do with what you want to use these benchmarking things for. Do you want to use it for learning? Because then you can play around with it in a much more flexible way than if you want to use it for contracts or controllability. It's of course also, as always, important to choose a measure that is easy to interpret and is easy to calculate, and you might even want to choose one that has a nice axiomatic foundation. So these are some of the guidelines for which measure to choose, and then the next presentations we're going to make are about how to actually estimate the technology. As you'll see, this one was about how to measure relative performance relative to a fixed technology, or given, maybe also dynamic technology, but a technology that was somehow given. Now, how do we establish this technology against which we want to compare? That's why we need DEA, that's why we need stochastic frontier, that's why we need Stone, and why we need other methods. But that's the next presentations. Okay, time for final questions, and then we'll break. And we break.